Hello, everyone. Welcome to Chemistry 132. I'm your instructor, Gary Rasmussen is my name. You can call me Professor Raz if you like. It's a little easier to say than Rasmussen. And I understand you want to be an engineer. I know for myself, I've always marveled at creations of man. If you take a look here, the very first time I golfed in Prince Edward Island, I had the pleasure of traveling over this incredible structure that's 13 kilometers long, the bridge to Prince Edward Island from the mainland. And I marveled at the beauty of it as well as its functionality. Incredible structure. The amount of time and energy it saves the people from Prince Edward Island be able to drive over there is enormous. It had a great impact on the island economically. Well, I too was a student at Queen's, and I remember what it was like to be a student. And this was where I lived in first year in Gordon House. I lived in 5th Gordon, and at the time it was an all-male residence. And we had some wild times there. And I recall time management was not one of my strengths going into first year university. And I'm going to help you become better at managing your time, because as first year progressed, I got stronger and stronger and stronger at managing my time, which is so important, especially as an engineer. You are going to be, I know how busy you are. And we had the greatest time there. So what got you interested in science in the first place? I know myself, my father was interested in astronomy, and he turned me on to astronomy at a very young age. This picture that you're seeing here, I hope you realize that it's a supernova explosion. And I was absolutely blown away when I discovered that little bits of blown up stars actually are inside all humans' bodies. They're inside all of animals' bodies. And that I completely marveled at that, because when stars are fusing smaller elements like hydrogen into helium, and helium and hydrogen are fused into lithium, gradually elements build up inside those stars over the millions of years of their existences. And eventually, in certain stars, if they have the right mass, right composition, they start to accumulate an iron core. And iron is the last element in the periodic table that's actually created inside those stars. And if the star has enough mass, not all stars, but some stars, will actually explode in a supernova explosion. And that is by far the most powerful, most energetic event in the universe. In fact, if the nearest star to us was to blow up in a supernova, it would wipe out all life on Earth. But fortunately for us, those nearest stars to us are not large enough. They don't have the right mass. They are not going to blow up into supernovas. In fact, supernovas can become visible literally millions of kilometers away from us. So just to remind you, any element that's inside the human body that's heavier than iron was at one point inside those stars. And that just amazes me. Now, whenever people were questioned about the greatest developments in engineering, in modern engineering, they always mention these two scientists. One of them on the left is a chemist. The other one on the right was an engineer. And their discovery completely revolutionized agriculture in the world as we know it. And what was that discovery? Their names are Frisch, Haber, and Carl Bosch. They learned how to produce ammonia, an artificial fertilizer containing nitrogen, from nitrogen in the air and hydrogen, which was taken from natural gas. What an amazing accomplishment. It's still widely used today, of course. We make large quantities of ammonia for use in agricultural fields to replace the nitrogen that plants use up. Plants, of course, have to make proteins, and all life forms require proteins. So the proteins, where do they come from? They come from amino acids. Well, amino acids come from ammonia, basically, and H3. So here's the chemical reaction that I'm going to show you a more detailed diagram of how it's produced, but they take nitrogen gas, hydrogen gas, they make ammonia, NH3, also called nitrogen trihydride. It's an exothermic process. Delta H is the enthalpy change under standard conditions, which the little degree sign means. It's a minus 91.8 kilojoules per mole, which means it's an exothermic process that releases heat. But it's not the heat we're after. It's the actual production of ammonia. The ammonia can be put back into the soils. And they won Nobel Prizes for that amazing discovery. Now, Nobel, I don't know if you know the history of Nobel, he actually developed dynamite, which itself was a major accomplishment. Again, another chemical engineering marvel. He actually took an explosive substance, which I'll talk about in a minute, and made it into a safer substance, dynamite. So here is the actual flow diagram showing the process. This is where the engineering comes in, figuring out how to take methane and water and then react it to make carbon dioxide and hydrogen, and then adding air, which contains oxygen. Nitrogen's about 78% of the air. Oxygen's about 19% of the air, 20% of the air, 21% of the air, depends on where you live. And then, of course, another chemical reaction happens. The methane reacts with oxygen from the air, makes carbon monoxide and hydrogen. So now we have a mixture. We have nitrogen, we have hydrogen, we have carbon monoxide, a catalytic reaction that goes through and it gets compressed and it gets scrubbed and it gets compressed again. They release water and carbon dioxide as a waste. The nitrogen and the hydrogen are then reacted. They're heated up. They're put in a reactor with a catalyst at very high pressures and temperatures, and they actually make the ammonia, the liquid ammonia, liquid gold, because of its effectiveness in stimulating plant growth. It increased crop yields all over the world. It actually sparked the green revolution. Now, again, I'm going to talk about Nobel's famous discovery. Prior to Nobel inventing dynamite, needless people died transporting nitroglycerin, a powerful explosive, to the actual sites where it was used, which were mainly mining sites and places, construction sites where they were blasting rocks. But Nobel actually created a safe version of the explosive by mixing the nitroglycerin with diatomaceous earth, which is made from diatoms. Diatoms are tiny little photosynthetic creatures that live in aquatic ecosystems. And he stabilized that nitroglycerin so it wouldn't explode. Now, if you think about it, where does that energy come from when nitroglycerin explodes? I know I've always been fascinated by what happens during explosions. And this is really where, when you look at a balanced equation, it doesn't tell you the whole story, but it shows a lot. It shows you that 4 moles of nitroglycerin solid suddenly make all these gases. Look at all the gases that are produced. From 4 moles, you're making 6 moles and 12 moles of carbon monoxide and 10 moles of water and 7 moles of oxygen. Look at the rapid expansion that happens. That's what creates that shock wave that creates the force behind the detonation and actually dislodges rocks and accomplishes all sorts of useful construction techniques. So that's Alfred Nobel's famous discovery. And he felt so guilty that his product was actually used for other purposes than construction that he donated a substantial portion of his fortune to the Nobel Foundation, which of course awards monetary quantities to famous scientists every year. And we always hear about them in the news. Wonderful way to promote science and engineering. So here's another famous chemical engineer. Actually, he wasn't a chemical engineer, but he was a biologist. His name was Alexander Fleming, and a wonderful discovery he made. And the rumor has it, and I don't know if this is true, but the rumor has it that it was a long weekend and people in his lab actually left early without cleaning petri dishes. A petri dish here, they were growing bacteria, and they left them over the long weekend, 3 days. When they came back, they noticed a fungus growing in the petri dish, and the fungus was making a region that was clear of bacteria. So they basically discovered that a fungus can make a chemical that kills bacteria. Well, my God, Bacteria cause disease in human beings. What if we can get rid of those bacteria? Well, that's when penicillin was discovered. And an engineer, this famous engineer here, Margaret Hutchinson Rousseau, actually figured out a way to mass produce quantities of penicillin. And penicillin, of course, saved countless numbers of lives, particularly in the world wars, World War I and World War II. So it was an amazing, amazing discovery. So now I want to talk a little bit about other famous chemical engineering discoveries. So I don't know, you've probably heard of nylon. In fact, we have a factory here in Kingston that makes nylon 6,6. Nylon 6,6 is made from adipic acid and hexamethylene diamine. 2 6-carbon monomers are pieced together to make this long chain reaction. And the airbags in all the automobiles, they all are made here in Kingston from adipic acid and hexamethylene diamine. And they're shipped in by railway cars from I think the New Orleans area. There are huge numbers of petrochemical plants there that create petrochemicals, and they ship them all the way here to make nylon 6,6. Now, the first nylon that was made was called nylon 6, and it was not made from 2 monomers. It was made from a single monomer. And they took this monomer, caprolactam, and they split it open using a catalyst, and then they created a polymer, which is a long chain of repetitive subunits, into nylon 6, which was a very valuable fiber. And again, here shows you the hexamethylene diamine. It's got 2 amine groups at each end, 6 carbons. This has a 6-carbon molecule. It's called 1,6-hexane dioic acid. So that's the IUPAC name for it, also called adipic acid, common name. And what happens is we link together the amine group of one end with the acid group of the other. Water is removed, so it's called a condensation polymerization. So if you take out an H2O here, you're left with an amide linkage, and we can accomplish it at both ends. So you make this long string of nylon 6,6 from 2 monomers. Now, other synthetic fibers, of course, were famous discoveries. So for instance, you can think of Kevlar, you can think of polyester, you can think of Dacron, you can think of spandex. All these are very, very useful fibers that have replaced the natural fibers that most of us take advantage of for clothing and for a huge array of various materials in our modern world that make life so enjoyable for us. Now, of course, the petrochemical industry is huge in how it's contributed to mankind in terms of producing all sorts of products that we need to power the world and to build different things. I know there's some environmental concerns, of course, but certainly the developments in our modern world would not have been possible without famous chemists coming up with new discoveries on how to separate the different factions of hydrocarbons. And for instance, methane is separated. Methane is, of course, natural gas. And we'll talk about that at some point in the course, how they actually use these fractionating towers and the difference in boiling points to separate the various components of a thick, gooey crude oil mixture. In fact, the first discovery of crude oil was in Russia, and it was dismissed at that time as a totally useless substance. This was in the 1800s. Could you imagine how wrong that individual was? When you think about the wealth that has been generated for various companies and people all around the world by processing petrochemicals and making all sorts of products from hydrocarbons. And of course, the pharmaceutical industry, so important to our survival. Think about the number of medications that people use that have extended life expectancies. If you go back 100 years, people only lived into their 40s, 50s. Nowadays, the average life expectancy in our country is something like 85. To a large measure, that was accomplished by the development of new pharmaceutical substances that we use to control our high blood pressure, that we use to fight all sorts of diseases. For instance, the COVID, what we're talking about now, the vaccines, which I'll talk about a little bit later. There are literally hundreds of thousands of pharmaceuticals produced by chemical engineers. We continue to develop new ones all the time. For instance, the new chemicals that they've just made for people who choose to be not vaccinated are saving their lives. They have just come online. Pfizer is making one right now that interferes with the reassembly of the virus proteins after it has been expressed from the RNA inside that virus. The RNA is turned into DNA. The DNA gets expressed into some proteins. And the Achilles heel of this virus is that it uses an enzyme that it expresses from its own genetic code that is not found in the human body. And these new pharmaceuticals block the action of that particular substance, and they stop the virus from reproducing. So if you get the infection, you still have treatments available where you can stop the virus. The vaccine, of course, works by simply stimulating the body's immune system so that you can fight the virus off very effectively. Now, of course, as I mentioned, vaccines, wonderful discovery, particularly the latest developments of the vaccines from messenger RNA. Previous to that, we used to use killed viruses, which we called attenuated. They would take the virus and disable it, but they would inject that dead virus into your body, and it would stimulate your immune system to fight the virus. And now they're using messenger RNA, which actually has a code in it that specifies the proteins that are made, so that from that messenger RNA vaccine, you express in your bodies proteins that are found on that virus. So there's no possible infection that can happen because it just stimulates your body to fight those particular proteins. And then along the way, of course, they start fighting the actual virus itself, and they control its growth so that we stay healthy. Of course, there is synthetic rubber, which was a huge development as a petrochemical, because rubber, we were running out of rubber. Rubber comes from latex from trees. We were cutting down these trees in the tropics, and we were running out of rubber. And how do we create all these tires for the automobile industry, which fueled the growth and development of the modern industrial world? Well, they invented a synthetic kind of rubber. They vulcanized rubber using disulfide bridges between the polymers in the rubber molecules. And of course, radioactive isotopes. I myself had a probe put in me a little while ago to take a look at, give me a better look at my heart. They put some radioactive isotopes in my body. And those radioactive isotopes, of course, as they decay by fission, they release small amounts of radioactive material that can be picked up by cameras. So they can take very precise pictures of your heart. And in fact, I remember asking the attendant to, hey, can I see, explain to me what's going on here? And he was putting as I was being probed, he was showing me my heart beating, and we were looking at the flow rates through my heart to make sure they were normal. And yes, they were all normal. So that was pretty exciting. But radioactive isotopes, a fantastic development of chemical engineering that enable us to probe the human body in ways that are so helpful to us. And of course, integrated circuits. You know, the silicon that goes in these chips is doped with tiny amounts of elements that have 3 electrons in the outer shell and 5 electrons in the outer shell. So the electrons can jump from silicon, which has 4 electrons in the outer shell. It can jump to little holes created where the element is arsenic, for instance, with 3, and integrated circuits were designed on that basic principle. Again, a chemical engineering marvel. Other engineers, of course, also contribute on a regular basis to the continued shrinkage of these integrated circuits. This particular integrated circuit here, I can't remember exactly how many there were, but there's literally tens of thousands of transistors in this integrated circuit here. It's just phenomenal, the process that they use to make these devices. And again, engineers are so vital to the development of all these wonderful modern conveniences that we have. Computers, of course, I've been using them for so many years, as you have. And I mean, I marvel at, I don't know what I would do without my phone and my computer and my tablet and all those things that depend on this integrated circuit technology, our automobiles. Now, I realize that you probably felt like this a little bit in first year. It can be completely overwhelming to study engineering at Queen's. But you know what? we have a lot of help available to you. Anytime you need help, you contact me. You know, I know there are over 800 of you in this course, but still I am willing to do whatever it takes to get you over that finish line and help you as much as I can. Now, please keep in mind with that number of students that are interacting with me, that I might take some time to get back to you at times. And if you have something that can be handled by your TAs that are running your tutorials, please use them as a first resort. And then if you're not getting the help that you need from them, then you can contact me and we can set something up. So now to get into just the logistics here of what we'll be doing, I want to basically just show you some other stuff that we're going to be doing. Okay. And everything on this course that I'm teaching you is going to be found on our homepage here. And on our homepage, what we have is OnQ. And in OnQ, the very first thing when you go in OnQ, which I'm going to be opening tomorrow, are our links to our YouTube lectures. So the YouTube lectures basically are on, I record them and then I upload them to YouTube and then I put links here, or you can simply find them. If you look at my name, Gary Rasmussen, and do a search, you will find me on YouTube. And I've been doing this for a few years now, recording videos and putting them on YouTube. If you are weak at particular aspects of chemistry and need some brushing up, feel free to look at any of my older videos from the 131J course, and they might help you, particularly when it comes to naming chemical compounds. In fact, I have a special lecture 1 for naming inorganic compounds, because I want to let you know that on your very first evaluation, week 4, the quiz, there will be a bunch of questions about naming chemical compounds. Now, I find just as English is vital to people learning about everything, you have to read to be able to learn things. In chemistry, in order to learn chemistry, the words are dictated by the chemical formulas themselves. So it's very important that you have this working knowledge of chemical substances, what I call your toolkit. Your toolkit is what is readily available inside your head. You don't have to look everything up. You should have some information inside your head that you can draw on very, very quickly, and it helps in the thinking process. So if you need help, you can try this special lecture 1, which is on our website right now. The first thermodynamics lecture, which will follow this one, is already uploaded up there. It's right here. And I want to show you everything else. Now, my view is a little bit different than your view. Your view is, for instance, there's things on here on my website that you won't be able to see. So, but I'm going to show you the stuff that you're going to see. So if you go to our 132 OnQ site, the main thing to look at is the content. When you look at the content, just want to show you the content here. We have everything on the side. We have a table of contents. If you look in your table of contents, you're going to see 144 items. And for instance, you know, the syllabus is here, among other things, but I want to show you the most important stuff. Like for instance, the units. If you click in the units, you're going to see the first unit, thermodynamics. It tells you week by week exactly what you need to do. Mastering chemistry is worth 5% of the course, and I expect you to do 10 assignments. Every week you're asked to hand in those assignments. Please make sure you work at them and don't fall behind. And then every unit has those items. Now, there are all the different units that are available, okay? And then I also want to talk to you about, in addition to the units, there are, okay, I'm just going to close this for a second here. Oh, sorry. So now in the units, there are appendices. So the appendices have all the problem sets for every unit. The problem sets are here. And in addition to problem sets, the very first thing I want to show you is the information sheet and the periodic table you'll be using with every evaluation. So get used to using these. In fact, anytime you're watching one of our recorded lectures, you should have this sheet printed out and you can see it. It's got all the formulas. Get used to solving all the formulas using this sheet. And also get used to using the periodic table. So the periodic table here, if you take a look, I'm just going to turn it, rotate it counterclockwise. Here it is, and I'm going to blow it up a little bit. Here's our periodic table. Now, this is a periodic table I made myself that is specialized for chemistry students. We won't be using the electronegativities and percent ionic characters this semester, but they were used in 131. These are the ions that you're given that you don't have to memorize. But I'm going to teach you a system where you can learn how to name and write the formulas for thousands of compounds by simply learning a system that if you can't memorize it, I've helped you out by simply writing these numbers on the table and show you. For instance, carbonic acid is H2CO3. So the number of hydrogens is given by the first number, the number of oxygens by the second number. So nitrogen, well, we have nitric acid is HNO3, one hydrogen. Phosphoric acid is H3PO4. Sulfuric acid is H2SO4. That's what those numbers are there for. So you can get all those different formulas from the periodic table I'm providing you with. Okay, fluoric acid is HFO3. Chloric acid is HClO3. Notice elements in the same family have all the same ratio. So really all I would have to do is show you for the first one, and you can assume they're all going to be the same. Similarly, selenic acid is the same formula as sulfuric acid, except replacing the sulfur, you replace it with Se. Okay, so now there's my special lecture on naming chemical compounds, goes over the development of all those. And I talk about my ho rule for learning these acids, where you go nitrogen, carbon, chlorine, sulfur, phosphorus, 1, 2, 1, 2, 3, 3, 3, 3, 4, 4. When you learn that little rhyme, it comes up with the actual formulas for these oxyacids. Okay, and you can watch that in the lecture if you may. I went over it rather quickly there, but hopefully you can get a gist for what I'm talking about. All right. Now I'm just going to go back. Whenever you want to get anywhere else in here, you go to content. And when you click content, again, you can find unit by unit, you can find the areas of study. Okay. Now, as I mentioned, there are course packs here. So course pack is basically, this is the course pack. Okay. Now, I know it costs a few bucks, guys. It costs a few bucks, but trust me, we're not making any money from this. Okay. This is the cost of binding all those notes together and printing them out. Now, this book doesn't have everything you need to know in the course. This, for instance, there are big blank pages. Okay. What I show you in our lectures is the solutions to these problems. So there are blank spaces that are left. Now, the course packs themselves, I don't have a copy of the whole course pack here, but unit by unit, I do have, if you take a look here, I do have, in addition to the course pack on the internet, I do have the lecture notes, and embedded in every unit are the lecture notes. Now, what the lecture notes are, for instance, the very first lecture is 1-1. The second lecture is 1-2. Okay, that's after this introductory lecture. So the first lecture, thermodynamic review. Here is a copy of what you can find online. Now, my expectation is if you couldn't get the course pack because the copy and print center was closed down prematurely, don't sweat it. Take your time. But if you buy one of those packs, which I highly recommend you do, then you don't have to print them out. But this is an example, like I said, there are blank spaces where you're going to be writing in as you listen to the lecture. Now, I wish I was in person teaching you, because I love communicating with people. But let's make the best of a bad situation. So there are some actual advantages to watching recorded videos. One of the advantages is for instance, when I show how to solve a problem at the end of the first lesson, there's a couple of problems, okay? There's one problem in particular at the end of the first lesson. And here's the problem. So what you can do is pause the video and then try to answer the questions on your own and see if you get the right answers. Now, if you don't get the right answer, then continue watching the video, and it shows you step by step in the lecture exactly how you arrive at all those answers. And then typically it has homework at the end of the lesson. This particular lesson doesn't, but almost all the lessons from that point on do. And then if you want to find the actual answers to those particular assigned problems, you can again look in your appendices. In your appendices, Appendix A, if you look here and see the appendices, in Appendix A are the questions, and Appendix B are the answers. So here we have, for instance, the problem set 1 in thermodynamics, and the answers would be found in Appendix B. So if you click Appendix again, and you look and see Appendix B, here are the solutions to the answers. Now, of course, we will be using our textbook by Petrucci, which is a wonderful textbook that you already have a copy of from first semester. And of course, there are answers in the answer book. So all the assigned questions, please try every question. I will guarantee you success in this course if you go through and try all those questions on your own and you solve them, because a lot of the questions in our evaluations will be designed from the homework questions. So solve those homework questions on your own, go through the struggle process. When you can't figure out how to do them, look at the answers in the answer book. If you still can't figure out how to do them, contact some of your colleagues and see if they can help you. And if you still can't do it, then you contact your tutorial guide, your TA. And then if you still don't get it, then you can contact me. So because, like I said, there's so many of us in this course that, you know, for me to deal with 800 people every single day is an onerous task. So please respect that and only rely on my help when you absolutely need it. And I will be available basically throughout the week. I don't necessarily have office hours. My office hours will be almost every day, except if it's snowing out and there's some nice weather outside. I'll take some time to go out and cross-country ski. Like yourself, I need time to unwind because I get pretty wound up at times. As you can see, I get very excited by teaching because I'm so thrilled to be part of your 132 course. I can't tell you how much I enjoy teaching chemistry. And just to go back here to my lecture, okay, I just want to show you again, this is what the beginning of that special lecture about naming chemical compounds found on the internet looks like. All right, so I'm just going to show you the different slides available. So I guarantee you, if you go through this step by step, if you're still struggling with naming chemical compounds, when you're finished, you'll be able to master writing thousands and thousands of formulas simply by learning those oxyacids: nitric, carbonic, chloric, sulfuric, phosphoric, the ones I was talking about. Ho, 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 ho. Nitrogen, carbon, chlorine, sulfur, phosphorus. 1, 2, 1, 2, 3, 3, 3, 3, 4, 4. When you get that, you can get all the other, you can get the us acids by taking one oxygen off, the ic acids, notice the ic acids, the us acids, and then you can take off another oxygen, you get the hypo-us acids, and then from there you can get the radicals, the polyatomic ions that are so important to learning all kinds of formulas. So those same formulas come from basically those polyatomic ions. So if you know nitric acid, you know the formula for nitrate. You simply take off one nitrogen. You know the formula for carbonic acid, you know the formula for carbonate. And once you know the eights, you can figure out the ites by simply subtracting an oxygen. So when you subtract an oxygen from the eights, you get the ites. And when you subtract another oxygen, you get the hypoites. So all of that I go through very, very carefully and much more slowly in that special lecture. So again, I thank you for for participating, and I welcome you to 132 Chemistry. And I'm assuring you that I will give you all the help you need to be successful. So I bid you good night. Thank you very much for participating here. It's been a pleasure.